Welcome to this lecture on journal bearing dynamics. My name is Roland Larsson and I'm a professor of machine elements at Luleå University of Technology in Sweden. We will discuss journal bearings, or hydrodynamically lubricated bearings, and their dynamic properties. The outline of this lecture is in two parts. The first part we'll introduce you to the problem, and then we'll discuss something called linear dynamic coefficients. And in the second part we'll do some mathematics and solve the eigenvalue problem to see where will the dynamics problem occur, and later also discuss how to solve them. Can we get rid of the dynamic problems? As you know, journal bearings can be found in many machines, very often in rotating machines for power generation. It could be hydropower, steam turbines, gas turbines, generators. Also in pumps and electric motors and combustion engines. And especially for example, in a hydropower plant like this, you have a vertical shaft. And in that case, stability problem may occur because the journal bearings for this machine is normally not loaded at all, or it can be preloaded. But on the other hand, the rotating speed of this machine is low, so you don't normally have any big problems with that. In a turbo machinery like a steam turbine as in this case, which may rotate at very high speeds, could be thousands or 10,000s of RPM, then you may experience, and this is very common, that you experience stability problems, and you must design the bearings to avoid them. So we are coming back to that. But why at all use hydrodynamically lubricated bearings in rotating machinery? Well, there are a number of reasons. And as you know, it's easy to assemble a large machine. They are smaller in radial size in comparison to a rolling element bearing. Have low weight, low cost normally. Contaminants can be embedded in the surface and have lower noise level, and they are also good for high speed operation. And which we will discuss here, they are very good in damping. They have much better damping property than a rolling element bearing. But again, a journal bearing or a hydrodynamically bearing may, even if they have good damping, they may cause dynamic instabilities, which is a little bit awkward, you may say. But we'll discuss this. Just to refresh a little bit the theory or the mechanisms of a journal bearing. This is a typical sketch of a bearing. You have the journal, you have the bushing, and remember that the journal is almost the same size as the bushing. It's maybe only differs here a part of a percent difference. But as the load is applied, a converging gap is formed here. So the motion of the journal will cause a pressure build up in the bearing, and this pressure is big enough to carry the load and separate the journal from the bushing. And when you start, or when the journal doesn't rotate at all, now we assume that the load is coming from vertically like this, it's only the mass of the rotor. In many cases, like in a turbo machinery, it's only the mass that is loading the bearing, so it's a pretty low load on the bearing. But at no rotation, the journal is just being at the bottom of the bearing, of course. Then when the speed is starting to increase, the gap is formed, and the journal is also moving slightly towards left in this case, because of rotation here to form this converging gap. And finally, if we run at very high speeds or infinite speed, you actually find that the rotor is concentrically located relative to the bushing. So, and on the way up from the very bottom to the center, the journal moves in a curve like this, which we call the attitude curve. Another thing to remember from journal bearing theory is that we two important parameters is the eccentricity and the attitude angle. So the eccentricity is the distance between the bearings center and the journal center, while the attitude angle is the angle between the vertical line, the load line. We assume the load coming down here now, and the position of the journal. So and then the minimum film thickness occurs in the direction of the eccentricity, and you can define a few important parameters here, like the relative eccentricity, which is normally used. That is the real eccentricity divided by the clearance, the radial clearance, delta R, and the minimum film thickness is then simply the delta R minus the eccentricity, or expressed in epsilon delta R multiplied by 1 minus epsilon. As you remember, when you do the design of bearings, you need to take a number of parameters into account, like the load, the speed, temperature, the radius of the bearing, the clearance, the width, viscosity, and you are searching for how thin will the film be, what will the attitude angle be, what the power loss, how much oil do we need to supply the bearing with, what will the operating temperature be, and also something called dynamic coefficients. And we come back to that later. When the journal rotates, the film is formed, and the film varies with the angle phi here, according to this equation. And you may also remember that you can use diagrams, design diagrams like this one, which they are always non-dimensional to make it general for many bearing sizes. So in this case, it's plotted the non-dimensional load bearing capacity of the bearing versus this relative eccentricity. And the different curves here show the different width of the bearing. So nu equals 1 means that the bearing diameter and the bearing width are the same, and these are more narrow bearings, and this is an infinitely wide bearing. So if we want to design, or we want to compute the minimum film thickness of a bearing, let's assume a real case here that we have a diameter of 200 millimeter, we have the width or length 100 millimeter. That means that nu is 0.5, so we follow this curve. We can also assume that the clearance is 150 micrometers, the viscosity is 21 millipascal seconds, and the speed is 3600 rpm. And what is then the minimum film thickness? Well, first of all, we compute the P naught, and P naught is just simply the real load multiplied by the psi squared, divided by the width, divided by the viscosity, divided by the surface speed of the journal. And the psi is the relative clearance, which is the clearance divided by the radius of the journal, and the surface speed is simply omega multiplied by the radius of the journal. So we put in the numbers here, and then we end up that the non-dimensional load P naught is 0.71, and we can read from the diagram 0.71. We go into the curve, 0.5 curve, and find that this bearing will operate with an eccentricity of 0.54. So that's the relative eccentricity of this bearing, and so the minimum film thickness is found as 69 micrometers. That's the basics in how to design a bearing, or how to find out if this bearing size is correct. Okay, but it's good. It's a good repetition before we enter the other points. Okay, now we'll put in some dynamics in here, because the diagram I showed you earlier was for stationary loaded bearings, static load. But there is always some dynamics in a bearing, because there are always some vibrations. There are, in a rotating machine, you always have some unbalance, and this unbalance will make the rotor to vibrate with the same frequency as the rotating speed. And you may also have excitation from other things inside the process, like in an engine or a crusher, or on some other machine with a lot of vibrations in it, dynamics in it. And then it's very good to have this damping effect of the journal bearing, because due to the squeeze effect, the oil is squeezed and it has some resistance from being squeezed out from the film. It provides good damping. But this damping effect may also cause, or actually the mechanism of the bearing, the lubricating effect of the bearing, may also cause instability. So even if it's a very good damper, it can still be unstable. Theoretically, you can solve Renner's equation, but then you need to introduce the time-dependent term, the dH/dt term, which we normally call the squeeze term. We are not going to discuss Renner's equation here, but you should be aware of that's the way to do it if you want to study the lubricant film in detail. But instead, normally what you do is to use something called linear dynamic coefficients. So you can describe, if you assume that the journal doesn't move very much, it maybe only moves 10-20% of the clearance, then you can linearize the dynamic behavior from in the statically loaded point. And when you do that, you realize that the film must be described by a number of springs and a number of dampers like this. And actually, there is a spring in the x direction, of course. So if you move the journal in the x direction, you get some stiffness response. But actually, when you move it in the y direction, you not only get a response in the y direction, you also get the response in the x direction. But because of the attitude angle curve, you remember that. So when the journal is starting, it starts from here and it rolls up like this in a curve. That means that if you add some motion, you will change the forces not only in one direction, you will change in two directions. So it's the same with the damping. The damping has a component both in the x direction and in the y direction for the x force, and the same for the y force, y direction force. This is the x direction and this is the y direction, by the way. So you can see here that you have 4 stiffness coefficients and 4 damping coefficients in a system like this. And again, these terms are interesting. These cross-coupling terms, or especially those 2 terms, are very important. That it's a spring that causes you cross-coupling. And these linear dynamic coefficients can be computed for any bearing, but for a cylindrical bearing, that is a plain journal bearing, you can compute them one time. For example, for a width to diameter ratio of 0.5, as we discussed earlier, you can compute non-dimensional stiffness and damping numbers, so you don't need to recompute them for another bearing size. And they are functions of the eccentricity only. This diagram can be used to study the stability problem. And the relationship between non-dimensional stiffness and dimensional stiffness is simply the ratio between clearance and applied load, and in the damping case the clearance and speed and applied load. This is the operating speed. So if you have these diagrams, you can do the analysis, which I will show you later too. As I said, we can there is an attitude angle curve like this, and this plot is maybe needs some explanation. In this case, I took away the journal completely, or I shrink the size of the journal to one point like this. So and then I can plot the clearance circle, what we call the clearance circle. So that means that when there is no rotation, the journal is down here, and when there is an infinite speed, the journal is up here. And on the way up, it moves like in a curve like this. So if you are in a position like here, if you increase the load, it wants to follow this direction. It doesn't want to follow just vertical direction. But now we assume that the load is coming from upwards. So if you just increase the load, you may expect that the journal will just move downwards, but it doesn't. It doesn't want to do that. It wants to move along this curve, and that means that you induce forces in both the x and y direction when you increase the load, and that is the reason to these cross-coupling terms of the dynamic coefficients. And here is the trick then. Here is the reason why you may induce instabilities. So this, if you try to move because of vibrations, you want to move the journal want to move in the y in the x direction like this. Then sorry, this is the stationary point. If it now it has moved due to vibration, this is a vibration orbit like this. It has moved some delta y distance from its equilibrium position, and that means that the cross-coupling term kxy wants to induce a force in the x direction due to this y displacement. So it wanted to move in this direction, and when it has moved a certain direction, distance delta x, it's the same thing then the kyx term want to move it in the y direction, and this will give you a kind of circular motion. So it's actually self-induced force that want it to move away from the stability point. It wants to circle around the stability point, and it may circle in bigger and bigger orbits, and finally it may crash into the bearing itself and destroy it. And in the next part we will discuss how to find out when this happens.